All right, good evening, everyone, and welcome to Mount Washington Observatory Science in the Mountains lecture series. My name is Brian Fitzgerald, and I'm the Director of Education here for Mount Washington Observatory. Thanks so much for joining us tonight. And joining us this evening to give us a better sense of atmospheric carbon dioxide is Dr. Ralph Keeling. He's a professor of geochemistry at Scripps Institution of Oceanography at the University of California in San Diego. So again, thanks so much for joining us tonight. For those of you who aren't already familiar with the observatory, Mount Washington Observatory is a nonprofit, member-supported organization with a mission to advance the understanding of the forces that create Earth's weather and climate. And we accomplish that through operating our Summit Weather Station with around-the-clock weather observation and forecast services, by conducting research and product testing projects, and by developing and offering innovative educational programs. If you have questions for tonight's speaker via Zoom, please feel free to use that Q&A button that you can find down at the bottom of your toolbar there on Zoom. We'll try and get to as many questions as we can at the end for a live Q&A session. If you're joining us on the live stream on Facebook, welcome. Thanks so much for joining us that way. Feel free, add your questions and comments there. We may not be able to get to those comments during the program here, but we'll try our best to respond following the talk this evening. If you'd like to connect with us through Zoom for our next program, please be sure to register over at mountwashington.org/SITM. Alrighty, well, before we introduce Ralph this evening, we will be launching a quick poll here. And for those of you who are joining us on on Zoom here, you will see a poll that is popping up at the moment. So a few questions for you, for those of you joining on Zoom this evening. First question, always curious where you're joining from tonight. Curious if you're joining from a state within New England, perhaps you're joining from outside of New England, and perhaps, as I suspect, there are quite a few of you also joining from outside the country. Curious to know where everyone is joining from. In addition to that, we're curious if you've joined previously for another Science in the Mountains program. Perhaps this is your first program. Maybe you've joined for at least a couple previously, or maybe you've joined many in the past, as we've been running virtually now for well over 2 years. And then lastly, we have a couple great questions from our speaker this evening. The first being, how much higher is CO2, carbon dioxide, today in the atmosphere than in 1800? 20%, 30%, all the way up to 60% higher. Get your guess in there. And then last but not least, over the past decade, atmospheric CO2 has been rising at a rate of 2.5 parts per million every year. So suppose the global fossil fuel usage suddenly dropped by half. Atmospheric CO2 would do what? Keep rising at 2.5 ppm per year for several years there? Would it immediately start rising at a slower rate, maybe half that amount at 1.25 parts per million? Would it immediately flatline and it would neither rise nor fall? Or would it rise for a few more years before flattening and eventually decreasing? Get your question or your responses in there. I'll give you just another 10 seconds or so to participate, and we can share some results with everyone. All right, and 3, 2, 1. Let's see what we have here. Alrighty, so if you're on Zoom, you can see some of the results now. Great representation from both the state of New Hampshire, almost a third of participants joining this evening from New Hampshire, another third from outside of New England. And then, hey, look at that. We have at least 4 folks joining tonight from outside the United States of America. Well, welcome to all of you, regardless of where you're joining from. And a nice little split here of folks who've joined programs in the past, and for almost a quarter of you, welcome for your very first program here. Hope to have you join again with us in the future. And then, boy, I think our speaker has given some pretty tricky questions for this evening. It looks like, well, we'll say most of you, at least 30%, the highest response got 60% of an increase in atmospheric carbon dioxide since 1800. And then more than half of you said if CO2 usage was if fossil fuel usage was to suddenly drop by half, well, most of you thought it would keep rising by at least 2.5 parts per million per year for several years before eventually slowing. So I don't have the answers to that right now. I have my guesses, but I'm going to let our speaker for this evening, Dr. Ralph Keeling, give those answers in his presentation this evening. And with that said, Ralph, I'd love to welcome you to the program tonight.
Yes, thank you, Brian, for that very fun introduction. I'm very happy to be here and speak to this diverse and interesting audience. I'll dive into some slides in a minute, but yeah, I mean, particularly the second question was a stumper, and we'll get to that. I did spend some of my years in New England, and I have fond memories of being on top of Mount Washington and seeing sunrises over the ocean and so forth. So I have a lot of pleasant memories caught up with the background that's on Brian's slide. So I've been there, done that many times. Huntington's Ravine and so forth. A lot of fun scrambles. So yeah, the story I'm going to tell tonight is a kind of a personal story, and it's in the context, of course, basically a global catastrophe crisis. It's easy these days to give a talk where you paint the grim picture and you say we got to act really fast to avoid something very unfortunate, and that could be the talk I gave, but I've shied away from that talk because I think most people have heard that talk a lot, and so I'm just going to talk about work that's kind of done in the trenches, getting data, thinking about what it means, basically back to the science here, but I do that without apology and without meaning to belittle the magnitude of the problem. I think it's easier it's important also to remember some of the details that are behind this. And there's a personal story here, mostly of my father, but a little bit of me as well, and my colleagues, of course. So let me start by sharing slides here. So that should. So did that come up okay? Yeah, okay. So there's
that looks great. Yeah, I'll let you, I'll hide away now. Thanks, Ralph. Sure,
there's my title slide. So yeah, this is my father's story. He grew up in Illinois, went to Northwestern for graduate school, had a degree in polymer chemistry, and was all set for a promising career in plastics, which of course was the future. But he liked the outdoors. He spent summers in Colorado as a child, so was very enamored of mountains and saw his future as living in the outdoors and particularly out west. He went then, and had spent a little time looking and studying geology, so he spun that sidetrack into his next move. He went to Caltech for a postdoc, and he still didn't know what he wanted to do exactly. He was given a project to look at uranium in rocks, which involved crushing rocks in a basement, not exactly outdoors, and that didn't fit his fancy too well. At some point, there was a suggestion by one of the professors, oh, I wonder what controls carbon dioxide levels in rivers. No one had thought about it. It was a good project because there are not very many rivers nearby Los Angeles, so we had to get in a car and drive around. This is actually a picture of a river in the Sierras, but he did work up the coast in Big Sur, looking at the carbon levels in rivers, but he quickly realized that to understand carbon levels in rivers, you had to figure out what was in the air, because that was an important control among several others. So he started to look at how to measure carbon dioxide in air. And at this point in the history, there was interest in whether carbon dioxide was building up in the atmosphere, but really not very much careful work had gone into it. And his focus initially was just to make a better measurement because he was having fun outside, and this was a complement to the river study. He learned very quickly, though, that the previous measurements had been much more, showed a lot of variability, but he was finding with newer methods that he worked out, that the carbon dioxide levels were actually much less variable, particularly if you got away from forests and you got away from cities and other influences, as though the background atmosphere, of the sort that you might probe sometimes on Mount Washington, for example, was much more stable. So the mountains figure into the story quite early on. Among the places he got samples was the White Mountains, the east of the Sierra Nevada, quite high mountains, 14,000 feet. And other places, he drove around the state and was surprised how regular the air was. The technique he worked out was really simple. The technique involved freezing the carbon dioxide out of the air using what was then a new high-tech material, liquid nitrogen, that became available commercially in that decade. And carbon dioxide condenses out of air at liquid nitrogen temperatures, so you can separate the air and then measure just by pressure, volume, temperature measurement, get a measurement of the number of moles of carbon dioxide in the air, and do a similar measurement on the original sample. You can get the mole fraction, the number of ppm. And this is a photograph of him later in life on a much fancier manometer that he built some years later. His newfound methods and newfound insight got the attention of Roger Revelle, who was the director of Scripps, and he was recruited to come to Scripps to carry out a program in collaboration, what was then called the Weather Bureau, to make measurements of carbon dioxide. And the vision was to do sampling around the world, do a massive survey, and using this more refined method. There was a little bit of a tension between Revelle and the Weather Bureau lead, a guy named Harry Wexler, over where to prioritize. And Wexler had set up a station on Mauna Loa. This is the Mauna Loa Observatory that is still taking measurements today, that it had just been set up then, and Wexler was looking for things to do there. And my father was very interested in that as a site because of his insight that if you went to a really remote site, you get a pretty stable value. And his hope was that with just a few years of measurements at one really good site, you'd see the whole atmosphere. You see carbon dioxide building up in the whole atmosphere. This had not been measured before. It was not clear whether CO2 was actually building up. It's not that people hadn't talked about it. Already in the 19th century, Savanti Arrhenius had come out with a paper that argued that fossil fuel burning would cause CO2 to build up and change climate. There was a scientist named Guy Stewart Callender who took that argument forward through the 30s and 40s, also did some rough calculations that showed maybe carbon dioxide was building up, but it was with the kind of imprecise and not well sampled data that had been available before. And just when Revelle at Scripps recruited my father, he was in the process of writing a paper that argued that really CO2 ought to be building up detectably. But it hadn't been shown. It was a theory. It was not a fact. Working mostly with Wexler at Mauna Loa, they set up an instrument after a while and started getting data. Now, I should say that at this point, he'd already developed a second method for measuring carbon dioxide that was much faster using an infrared analyzer. But that analyzer system still relied on the liquid nitrogen approach, so-called manometry approach, for its high-level calibration. So it was a hybrid approach. But the instrument on Mauna Loa was an infrared analyzer of the sort that was being used. I think it was developed maybe by the Germans for air quality on submarines. It was used in mining operations. So there were already industrial applications of this analyzer, but no one had trained it on background air before. It's like Galileo being the first person to point a telescope at the heavens. Telescopes existed before, but he pointed it in a new direction. My father was pointing a new instrument in a new direction. So here's a photo of the Mauna Loa Observatory some years later. This is a 1982 photo. Off in the background, you see a mountain. That's Mauna Kea. That's the other big mountain on Mauna Loa. I'll say a little bit more about that in a minute. So there's the station. They set up the analyzer, and the data started streaming in March 1958. And the readings looked about like this. So they had the data was scattering around a little bit, but actually not very much, just barely a range of a couple parts per million, really quite precise measurements. And over the course of that month and a half or so, it pretty much just showed one level. And it was sort of confirming his notion that, wow, that's a really stable reading. Maybe in a year or two, we'll be able to see if it's changing, see if it's building up. Of course, as always happens when you start something for the first time, things go wrong. And what went wrong was the generator failed and they had no power for a while. And they eventually got the generator back on, the instrument came on, and now what? CO2 started off at a lower level and was no longer stable, it was dropping. He had no idea why this was happening and imagined that it was some defect in his instrument, but he didn't know what it was, so they couldn't fix it because he couldn't diagnose what was wrong. Another power failure, and the power came back on again. CO2 was even lower, and now it was rising. So it looked like his dreams for precise measurements were not being realized. There was something erratic about the instrument. He didn't understand it. So this was a frustrating time. Again, he didn't have a diagnosis, so they just kept it on. At this point, the power was a little more stable. And about this point in the second year, you could look at this pattern and realize that it was repeating the pattern from the year before. So there was a discovery here. The discovery was that carbon dioxide was going up and down with season. For whatever reason, in 100 to 200 years of prior measurements, no one had seen this regular pattern before. And of course, because it was quite a regular pattern, it was indeed possible to see a buildup after just a few years. And now with the continuation of that record, this is what it looks like. So the levels around 315 at the beginning of the period, building all the way up now, pressing up towards 425 parts per million. And yes, you see this regular cycle, up and down, up and down, up and down every year. What's that cycle? Well, it makes sense. Carbon dioxide is taken out of the atmosphere by plants in the summertime and by photosynthesis. And so the CO2 is drawn out of the air. Other times of year, there's plant matter that's decomposing, releasing carbon dioxide back in the atmosphere. So it's a natural cycle of life. And that natural cycle is now superimposed on this very persistent and really ominous rise. And even after a few years, you could see the rise. The record didn't look like it does now. I mean, having watched this record over years, it always goes from the lower left to the upper right corner of the plot. And the rise over time progressively dwarfs by more and more the natural cycle. So we're seeing the dominance of human intervention in the system on the natural background. Now, important developments followed this, including interest in what had happened to carbon dioxide in earlier times. And I'll show that in a minute. But as some of you may have heard in the news, the Mauna Loa volcano erupted in November. Here's a photograph of that. The observatory is not in sight in this, but it's behind this white cloud back here somewhere. The observatory was not touched by the lava flows. However, the access to the observatory, which is along a road that traversed somewhere along here, I can't quite see it, got buried by the lava, and the power supply to the station, which was just regular power poles, also got cut. So between one day and the next, we went from having data and access to the station to having no data and no access to the station. I should say that, what's my role in this? I joined my father spent his career at the Scripps Institution of Oceanography. I joined the faculty there in 1993. I carried out a parallel program to measure changes in oxygen in air, which I'll tell you about But when my father passed in 2005, I kept this particular measurement and several other measurements going because they had such great long-term value. What happened? So the Mauna Loa Observatory is run by the National Oceanographic and Atmospheric Administration, which was the eventual outgrowth of the Weather Bureau. Together with the staff at NOAA, we scrambled to try to put an instrument on nearby Mauna Kea, which had never been done before. Because the Mauna Kea has an astronomical observatory on it, so it has good logistics. It was necessary to get permission from various people to do that. The visual footprint of the CO2 measurements is nothing compared to the big observatories on the top, so there was not really any issues with native concerns of the native Hawaiians. And so after about a month, or actually a matter of weeks, we got an instrument going on Mauna Kea. And so here's the Mauna Loa record. Here's the interruption in November from the volcanic eruption. Here's the beginning of the Mauna Kea record. And then by March, mostly because of the diligence of the staff at the NOAA Observatory, they were able to restore power to our instrument using solar panels, accessing the station entirely by helicopter. So we still don't have power to the station on the ground. We still don't have a road, but we do have an analyzer running. So this is the continuation of the Mauna Loa record now. And although not shown on here is we also have the Mauna Kea record going. And we haven't looked in detail at the differences, but the overall patterns are actually very similar. Not too surprising because it's pretty close, and the elevation of the sampling on Mauna Kea is similar to that on Mauna Loa. We do see differences though, and we'll have to sort that out. But our hope is that we can use these data after an intelligent assessment to fill the gap. Now looking into the past. So here's the Mauna Loa record. It became possible in the 1980s to recover air from Antarctic ice cores that provided CO2 levels in the atmosphere prior to my father's measurements that were also reasonably high quality. And what they show is that when my father started measurements in 1960, CO2 had already risen from a natural background level of around 280 parts per million. So here starts at 280, and the present levels are about 420. Okay, so you can do the math there, but it's about 50% increase. Okay. And this stable background level, which persisted for centuries and even thousands of years, of around 280, was also superimposed on natural fluctuations of carbon dioxide rising and falling associated with the ice ages. And these take us back to about 800,000 years. So you can see here's this last period here where it's only going up slowly. That's actually the stable levels of the Holocene. Here's the rocketing upwards from human activity. And these are natural fluctuations associated with changes in the Earth's orbit, how much the orbit is tilted and how much sun you're getting at different times of year affects ice sheets, and ice sheets affects ocean circulation, which affects carbon dioxide. So the carbon dioxide is being driven up and down by orbital changes. That takes us back to 800,000. That's as far as we have really good data. You can go further back with so-called proxy measurements. There's inferences of carbon dioxide you can get out of looking at the behavior of leaves, looking at isotopes in marine organisms and organic compounds in marine organisms. So here's some reconstructions going further back, and you can see the recent levels are not the highest the Earth has ever seen, almost for sure not. It looks like, particularly if you go back 30 million years ago, CO2 levels were a fair bit higher. We may already, however, be breaking through the high levels that were back here in the Miocene. So it's possible there were levels as high as today, millions of years ago. This is sort of the very beginnings of human evolution back here. So this is really long ago, and this is back when the dinosaurs, well, a little bit before that, when the dinosaurs went extinct. So this is really distant past in Earth's history that the territory we're pushing into. So let's talk about the relationship between this and fossil fuel burning. There was really never any doubt that fossil fuel burning was the main thing responsible for the rise. The reason for that is we know how much fossil fuel we're burning every year from fossil fuel burning. You can do the math. You can calculate how much CO2 would be increasing if all that extra CO2 stayed in the air. And what you find is that CO2 would be rising almost twice as fast as it actually is. So the question wasn't why it was rising. The question was, why isn't it rising faster? Where is the extra CO2 going? Why isn't it all building up in the air? So the quest was for understanding these so-called sinks. Why is part of the Earth system soaking up CO2 that's not staying in the air? And so a lot of work preceded this to try to figure out where this extra CO2 is going. So the basic picture is simple. So here's the atmosphere. The CO2 is being emitted from fossil fuel burning. That's going into the air. So where can the CO2 be going? Well, really two places. What's the land surface got on it that can soak up CO2? Well, it's got the oceans, or the Earth's surface has oceans, and the oceans have a capacity for absorbing carbon dioxide. So there's a logical place for some of it to go. And of course, vegetation can soak up CO2. So that's another possibility. As work progressed, it became clear that actually the impacts of humans was not just restricted to fossil fuel burning. We're also clearing land for agriculture and various other purposes, leading to emissions of CO2 from land systems. So we recognize these four basic processes: fossil fuel burning, ocean and land sinks, and land use. And it's the residual of all of these that is causing the buildup of the atmosphere. And these processes are offsetting about half of fossil fuel burning in aggregate. Now, let's see here. It's just the same thing. So, let's see here. I'll go to this. I'm out of order here. So, let me go back to this. Okay, so what was clear when my father was making these measurements, and is still really the most solid part of the story, is we know how fast CO2 is building up. So we know the buildup. We also have pretty good inferences of how much CO2 is coming from fossil fuel burning. So we know that, those two contributions, and therefore we can also calculate by difference these different contributions here. The challenge was to separate them. How much was going into the ocean by itself? How much was going to the land by itself? And it turns out there's various ways that can be done. A method that I particularly focused on involves looking at changes in atmospheric oxygen. So as you burn fossil fuels, you're of course taking oxygen out of the air. You're oxidizing the fuel, making carbon dioxide. And so the exhaust pipe of your car has extra CO2 in it. It also has less oxygen in it. So we're slowly depleting the oxygen in the atmosphere as we're burning fossil fuels. The oceans take up carbon dioxide mainly because of inorganic reactions like of the sort written here. There's no oxygen involved, so this doesn't affect oxygen. But to the extent that plants are growing, or there's plant material being decomposed or burned, you have impacts on oxygen. And how can we get a separation from this? Well, there's different ways of describing it, but it's helpful to actually look at how these processes affect the sum. That is the combination of oxygen and CO2. It turns out when a plant grows, it takes in CO2 and it puts out almost exactly the same amount of oxygen as CO2. So it removes CO2 and puts oxygen back, but it actually doesn't impact the sum of the two in the air. And then this land use won't really either. Fossil fuel burning does impact the sum a little bit because it turns out there's more oxygen loss when you burn some kinds of fossil fuel than there is carbon dioxide production. That's because some of the oxygen loss is going into producing water. You know, the exhaust in your car is also very, very humid. That's because you actually chemically produced water by burning hydrogen in the fuel. So there's actually, this does affect the sum, but we know that because we know the composition of fuel and we know how much fuel is being burned. And so if you correct that sum for this process, you can get and measure the sum, you can actually calculate the ocean CO2 sink by what's left over. And I, early in my career, I set up stations to get air samples to measure transit oxygen. And this is what that data looks like. Here's carbon dioxide levels going up in the atmosphere in this lower plot. And here's oxygen levels going down. Don't worry about these units. We don't need to focus on that, but oxygen is decreasing. We were able to show that, and we were able to quantify it very precisely. And the sum is also decreasing at a rate that's faster than we expect from fossil fuel burning. And that excess loss of the sum quantifies ocean CO2 uptake. So let me just put an aside here. So, big news story, oxygen's going down. You haven't heard about this. Well, that sounds bad. We all need oxygen to breathe. Shouldn't we be worried? And the answer is, well, it's not that big a deal because there's so darn much of it. And what we're doing with fossil fuel burning can't really cause an environmental problem. And to put that in perspective, let's just look at magnitude. So here's the amount of CO2 in the atmosphere represented by a circle, and here's how much we would be putting in 10 years of current fossil fuel emissions. So it's certainly in many decades, you can have a substantial increase in atmospheric CO2 by this contribution. That's the problem, okay? But let's look at that in oxygen. The oxygen reservoir of the atmosphere is huge because it comprises almost 21% of air. 10 years of fossil fuel burning will make a dent in oxygen of this amount. Even after many decades, you've hardly touched the oxygen levels in the air. And moreover, if you look at even large estimates of the fossil fuel resource base, they're sufficient to make a massive change in atmospheric CO2, but only a small dent in atmospheric oxygen. So we run out of we run out of fossil fuel by any reasonable scenario long before we run out of significant amounts of oxygen. So it's important to measure oxygen as a diagnostic. It's not, however, a legitimate environmental concern. And here's what the numbers show. This is a budget for the decade of the 2000 to 2010. We could do it for the more recent decade, but it wouldn't look very different. Where is CO2 coming from? It's mostly fossil fuel burning. The land use emissions are a small addition to that. And that has to add up to where all the CO2 is going. CO2 is going in the atmosphere. We're measuring that. The oxygen uptake is measured by, the ocean uptake is measured by oxygen, and then you can calculate how much has to be going somewhere else into the land to make it up. And what's interesting about this is that this confirms that the land is actually soaking up CO2. That was not believed to necessarily be the case early on. People were focused on slash burn agriculture and all these things that would cause CO2 to come off the land. But it's really by looking hard at these numbers that we were forced to recognize that the importance of the land as a sink for carbon dioxide. In fact, overall, there's more carbon dioxide being taken up than there is being emitted. So the land as a whole are soaking up CO2. That's perhaps kind of obvious, right? Plants take up CO2. Why should that be a surprise? Well, it turns out plants do, but it's not obvious that a forest does. So, okay, let's talk about growing a forest. What happens? You start with bare ground, you plant a tree, grows, and there's CO2 being taken up, right? It's photosynthesis. Where did the carbon go? Where's the carbon that's no longer in the air? The answer is still there. It's not in the air though. It's in the tree. It's in the carbon, it's in the trunk of the tree, it's in the roots of the tree, and maybe in the soil where the carbon accumulates. So the reason you're taking up CO2 is because you're actually piling up carbon on the landscape in various forms, particularly tree trunks. Now, of course, in a forest, you don't just have trees growing, you have trees that are old and decaying and dying, and what's happened to them is they're actually releasing CO2. So there's also a breakdown going on. So the overall a forest where both are going on, that's kind of in a natural state, you're releasing as much CO2 as you're taking up. The cycle of life is a do-nothing loop. It's not taking up CO2 from the atmosphere, it's a do-nothing loop. Well, it does a lot of good things, but it doesn't take up CO2. So we know that the land is taking up CO2. What does that mean? It means something is out of balance. So something involving human activities has tipped the system out of balance. So the land is landscaping is soaking up CO2 in a way that it didn't before. A lot of interest in trying to figure this out because this is helping us solve the climate problem. Not because we did anything on purpose, because Mother Nature kicked in and did something surprising that's helping us. One of the reasons it's doing that is because carbon dioxide actually stimulates growth more than it stimulates and doesn't stimulate decomposition. So the balance has been upset just because there's more CO2 in the air. It's also being upset because we're warming landscapes that are providing places for vegetation to grow where it couldn't really grow before. we do have other indications that something is out of whack on land or out of balance. I mentioned the cycle in carbon dioxide going up and down at Mauna Loa. Well, if you look at stations throughout the Northern Hemisphere, you see similar cycles, but further north, you see even much bigger cycles. That's because you're actually closer to the boreal forests, which are the kind of the main, and the temperate forests, which are where most of the carbon dioxide has been taken in and out of the Northern Hemisphere. And particularly Barrow, Alaska, where we have data going back all the way to 1960, you can see that the swing up and down this season has almost increased by 50%. So it's as though the land ecosystem is hyperventilating. It's becoming more and more active over time. So also in these CO2 records, we see evidence of big shifts going on in the landscape affecting carbon dioxide. And just to put this in perspective, this is what the North Slope looks like now. This is probably the North Slope of Alaska. Tundra, it's a tundrascape. What did this look like when you go back to the Pliocene? Well, it turns out the boreal forest went all the way to the Arctic Ocean, and we're pushing probably towards that kind of climate state. So this kind of landscape, over time, we can expect will grade towards this kind of landscape. Vegetation that can pull carbon dioxide out much more efficiently than this. So the warming of the Northern Hemisphere high latitudes is definitely promoting an increase in the seasonal uptake of carbon dioxide. So there's partly a warming story here too. Okay, so let's go back to this curve. So this is the rise in carbon dioxide. And this is what would have happened if nothing had gone on except fossil fuel burning. And where is that other carbon dioxide going? Well, it's going into the land and the ocean. So this is the land and the ocean are pulling out carbon dioxide, pulling it down. Why are they doing that? Well, they're doing that because there's extra CO2 in the air, among other things. So let's talk about what happens if you suddenly cut, and I should say that the rise rate is about half of the emissions, so that the sink is basically taking away half of the emissions. So what would happen if we cut emissions in half? Well, the answer is for the first few years anyway, the sinks would just keep going. They're not a direct response to emissions. They're a direct response to how much CO2 is in the air. And there's still a lot of CO2 in the air. So the sinks are going to persist. And they're going to be strong enough to take up 50% of what we used to emit, which is now 100% of what we emit after we cut by 50%. So we flatline it. So if you cut CO2 in half, CO2 emissions in half, what would happen basically right away, because there's no delay, it's whatever you put in, what you take out, it's a difference that's accumulating in the air. That difference immediately goes to zero. So CO2 levels would flatline. So that if we cut it in half, this curve would just start going straight over. Now, I wouldn't keep doing that because the sinks eventually would slow down. And so we'd have to cut more to keep it from rising anymore. So if you want to keep CO2 at a constant level, you have to basically cut by half and then progressively cut more and more over time as the sinks slowly lose their power to soak up. It's like a sponge soaking up. They'll soak up for a while, but eventually they'll kind of saturate. We don't understand the details of that in every respect, but that general behavior is inevitable. So I haven't said very much about temperatures here, and I have one more slide just to touch on the topic. But I'll point out that there's clearly a sort of complicated relationship between emissions and what's built up in the air. I don't think more than about, from what I saw in the answers, more than about 20% of you guessed the right answer there. So we recognize that that's complicated. There's a simpler complicated relationship between how fast it warms in response to how much CO2 is in the air. So both of those connections are complicated. But it turns out if you throw it all together and you combine the information the right kind of way, you get a simplification. And this simplification is heavily guiding discussion today. It's guiding discussion, for example, in making it relevant to talk about net zero. So let me explain that if I can in one slide. So this is a slide that reduces the system to kind of an abstract coordinate system. So this is on the y-axis here is how much the Earth as a whole has warmed relative to some natural level that say persisted in this time frame in the 19th century. This is how much the Earth has warmed. And on the x-axis is the total amount of carbon dioxide we've emitted, basically from fossil fuel burning plus land use, but dominated by fossil fuel burning since that time frame. So this is not how much, the equivalent for your automobile wouldn't be how much gas you're burning in a day. It's how much gas you burned since you bought that car. What's the total number of gallons? And of course, as you continue to use fuel, you keep going, even if you cut your emissions, you're still going to the right because you're still using more, you're still adding to the total you have used. So it's very hard to move to the left on this diagram unless we actively scrub CO2 out of the air. So as time progresses and we mine more fossil fuels, we move to the right. And what this shows is that over a range of scenarios that have different future emission pathways, including ones that have lots of emission going way up to high levels and ones where you cut emissions over the next few decades closely down to zero, they tend to collapse onto a fairly straight line. So there tends to be a proportionality between how much the planet has warmed and the cumulative emissions. And this collapses both of those complications I mentioned before, how the buildup in the atmosphere is a complicated response to emissions and the warming is a complicated response to the buildup in atmospheric CO2. But those complications somewhat remarkably cancel out if you do a plot in this way. So what this tells us, for example, and when this diagram was created, I think when was this? 2017, the emissions of fossil fuel the cumulative had been something like 550 of these units. These are billion metric tons of carbon. And the warming was about at this level. And if we wanted to keep CO2 from going to 2 degrees, there's a maximum allotment we can emit. If we emit beyond about twice at that level, so go beyond about 1,000, we've already crossed that two degree warming point. So how does net zero fit into this? Well, net zero is the point at which you're no longer moving to the right on this diagram because you're taking up as much as you're emitting. So you're not moving to the right. So the idea of getting to net zero is to get to the point where we're no longer making the problem any worse. So net zero isn't where we solve the problem. It's where we get to the point where it's not getting worse. And you can see that, for example, if we want to cap emissions at warming at 1.5 C, which some people have talked about being a dangerous threshold, we don't have much of an allotment yet. It's very hard to imagine how we could possibly do that. Even 2 degrees C seem pretty difficult. My own sort of, what do I think is a reasonable scenario for what might happen, even if people are acting with some level of responsibility, is that about the point where people really start bending the curve, the warming will probably go up by about twice what it is already. And that's because I think it's reasonable to speculate that we could cut emissions over time as fast as we grew them in the first place. Infrastructure has changed that fast. It could change that fast without huge disruptions. But that would mean, because we burn as much on the way down as we did on the way up, that the cumulative emissions will eventually be twice what they are today and the warming will be twice what it is today. That's not a happy scenario, but if I had to bet on it, I would say something like that is reasonably likely to happen. And it's not a pretty picture, and which is why people are trying to find ways to push this to go even faster. So with that, I think I'll stop and happy to take any questions. I'll stop sharing for the moment.
All right. Well, thank you so much, Ralph. I appreciate it. Though I have to call you on it. I feel like you did end a little bit doom and gloom just there. I mean, it was both a little hope and perhaps a little doom and gloom.
Yeah, sorry about that.
Yeah, that's all right. I appreciate it. But Yeah, as Ralph mentioned, certainly would love to offer some questions. I know I have my own. I don't want to hog all of your time. So if you are joining us on Zoom, please be sure to get your questions in using the Q&A button that you can find there on the Zoom toolbar. I know there was one pretty early on actually from Nina, who was asking a question, Ralph, um, about a little bit about human respiration and its impact on CO2 in general. So the question from Nina is, given human population has also risen over time, possibly along with more domesticated livestock, over time, how much does our respiration, they might be meaning both livestock and humans, contribute to CO2 in the atmosphere? Do you have a sense of that, or how that might play in?
Yeah, I mean, two pieces of it. First, human respiration is detectable as a component, say, in an urban environment. As you can obviously measure it in a room, and you can measure it in a city. But remember that your respiration was fueled by food you ate. The food you ate was a crop. The crop grew by taking CO2 out of the air. So by respiring, you're just completing the cycle of life.
Mm.
That's a do nothing loop with respect to CO2. So that's a sustainable loop. That's really not an environmental concern for that reason. First of all, it's not big, and second of all, even if it were, it would be part of a do nothing loop. So it wouldn't cause a buildup, because you're not eating fossil fuel. If you lived off like a microbe that could digest oil, let's suppose we ran out, we couldn't grow food, and we decided, oh, we can just live off petroleum. That tastes great, man. Then we'd be part of the problem. But as long as we're living off things that we're growing in the atmosphere, we're okay from that standpoint. Now, bear in mind that agriculture requires fossil fuels, so there are other costs. But the food itself, the respiration itself, is not the issue.
Yeah. Okay. All right. That's where I was tripped up for a second there. I said, wait a minute. There's fossil fuels involved somewhere in that process. Well, in relatedly, an anonymous attendee was asking a little bit about methane, and if, just generally how methane, I mean, so you're mentioning CO2 being one of the contributing factors to the, accelerating greenhouse effect, methane being another one of those, classic, if not in some ways more, I guess, I don't know how you might phrase it, acutely impacts, or is a even more powerful greenhouse. Oh, I'll let you describe that, not me.
Yeah, no,
Yeah, how does that factor in here as well?
Yeah, I didn't talk about the other greenhouse gases, which do matter and they're important. They collectively contribute about 50% of carbon dioxide, individually considerably less. Methane is more potent as per molecule than CO2 as a greenhouse gas. Of course, we're emitting a lot less of it. So in aggregate, it's less important, but still important. It's different in its behavior. It goes away quickly. So the endpoint of mitigation for methane is probably not emitting no methane. It's emitting at the same amount so that it's being decomposed as fast as we're emitting. So it doesn't build up in the air in the same way carbon dioxide does. It sort of reaches quickly a steady state with emissions. It doesn't build up anymore. But that's still a problem if we emit more and more, which is what we have been doing.
And then even another greenhouse gas being, I guess, the general synthetic greenhouse gases being produced, CFCs, and I guess of the sort that, correct me if I'm wrong, but those have even longer lifespans in the atmosphere, but perhaps we're not producing those as readily as CO2 or methane.
Individually, they're mostly pretty minor, but when you add them all up, and there are a lot of them, they're important. So they need to be regulated. And the other big one is nitrous oxide and N2O laughing gas, which is a byproduct of the nitrogen processing in soil, which humans, of course, have had a big impact on through the production of fertilizers for producing the green revolution and the food we eat. So that's a really tough one to solve, because we do need the nitrogen fertilizer. We probably don't need as much if we would get smarter about how we use it. So there's room to mitigate there, but that's definitely not the low hanging fruit for mitigation.
Sure. Well, and I'm curious as well. I mean, so Justin asked the question. I know certainly you spoke about really in doing the grand summation of all the different contributing factors of CO2 and how sinks and other sources. But in the oceans, what is the impact happening there? I mean, essentially, what's the impact related to acidification?
That's a good point. By the way, thanks for that question from Justin. I should point out that it's nice to have acquaintances in the audience. And Justin Lancaster was a graduate student of my father's. So you have a mole in your audience who's an insider pretending not to be.
They show up from time to time, yes.
Anyway, so hi, Justin. Yeah, so ocean acidification. So yeah, there are impacts of carbon dioxide on the system that go beyond the radiative effects of CO2 and the effects on climate. There's really three effects you can count. I mean, I already mentioned one. CO2 is actually causing plants to grow faster. So and mostly we consider that a good thing. But of course, if we're changing ecosystems by making it take up carbon, there'll be consequences. So there's almost certainly environmental consequences to the benefit we get out of ecosystems taking up CO2. In the oceans, the concerns are even a little greater because the CO2 changes not just how photosynthesis works, but particularly changes the ability of organisms to grow shells out of calcium carbonate. You'd think that with more carbon in the air, there'd be more carbon in the water, and that would help things that live off carbon. It's actually backwards. And that's because CO2, in this case, that's the most relevant property is that it dissolves as carbonic acid. So it's an acid, and acids, if you ever put lemon juice on a shell, you get bubbles. You're corroding it. So it's corrosive to shells. So it makes it harder for shells to grow. And that includes corals and other things that are in the food chain. And so that's a really important active area of research and one to definitely pay attention to because it's concern.
Yeah, absolutely. And it kind of makes me wonder as well. I know there's someone asking similarly, given that you're at Scripps, how has CO2 content in the ocean changed over time? Well, I'm curious even more broadly. I mean, not being so familiar with all the work happening at Scripps. I mean, where does your research fit into, say, some of the other research happening within that broader institution? And, where do you see other sort of points in connection and sort of the bigger research questions here?
Yeah, that's a really important question. I'm one player in a community at this point of thousands, and even hundreds are involved, maybe more, in making these kinds of measurements. So this story I told highlights the iconic record, and in some ways the most important of all the records. But they're carbon dioxide being measured by different programs around the world. There's interest, for example, in using measurements in the atmosphere of this sort to get a better handle on whether mitigation is actually working, and drilling in not just to whether the world is on track, but whether individual cities and other jurisdictions, countries, counties, and so forth are on track. So we can use the atmosphere as a kind of proving ground for whether we're actually doing the right things. In terms of the oceans, yeah, there's a lot of work trying to understand these impacts. We also, sorry,
All right.
I'm being called off. So the oceans have a lot of important roles to play going forward, and we need to understand them. There's a lot of discussion now about trying to enhance carbon dioxide removal by the oceans through various mechanisms. Do we know they're going to work? How do we prove they work? There's a lot of need for better understanding there. And the oceans also are important because they're reducing the warming by taking up heat. So they're buffering the carbon dioxide rise. They're also buffering the warming. So we're getting huge benefit out of the oceans, but in some ways, when we stop emitting, those benefits also taper off. So they're part of the approach to the endpoint. Also, we have to understand that as well. There's so much I could say there. I probably should just.
Yeah. Oh, I'm sure it was open-ended for sure. I mean, I'm curious always how how scientists see how their work fits in and connects. I mean, not only elsewhere in science, but hopefully a connection point to people living their everyday lives for sure. And you've been thinking about a lot of these topics, I'm sure, for quite a while. I mean, you're carrying on a legacy started by your father as well, which I'm sure has some personal weight to it. which I can't imagine, but I'm sure at the same time, you know, is really special and meaningful to your work.
Yeah.
Not a question, more just a more just a comment in general.
Yeah, I mean, I guess the question would be, how did I get here, and why did I let this happen to me? But you know, I had fun measuring oxygen, and I was at Scripps when my father passed, and I took on his program, and that's been fun too. It's been educational and it's been rewarding. So, and you know, it's being watched by lots of people. So it's important for us to get the message out and keep a clear message. I mean, this is one of the easier, simpler stories to tell. So it's also an entry point for people. It's hard to argue with what's happening with carbon dioxide. When you absorb the magnitude of what's happening, you realize, yeah, this is a big issue. So you get to that realization rather quickly through carbon dioxide.
Yeah, well, certainly personally grateful for the work that you contribute to from an educational program standpoint. I mean, even my own schooling and countless other people across the planet, the Keeling Curve is one of those pieces that's it. That's what you're showing. I mean, yes, you've shown the connection, how it fits in the longer span, the ice core data, proxy data, how does it fit into the bigger picture? But at any rate, an important piece of data. And for those of us at the observatory here, always amazed how other people operate in other stations, always curious when other people are operating in other funky places. And, you know, when we saw the eruption in Hawaii, it certainly made, I'll speak for myself, made me feel like maybe some of our challenges weren't quite as tough here on Mount Washington. We don't have to deal with that at least. So that's a nice thing. Just one last question for you. I'm sorry if I'm skipping over some questions here and sort of stealing it a little bit, but I'm just curious from an instrumentation standpoint. I think I saw a really neat video, maybe you actually you maybe taking some CO2 measurements. And I'm curious just from the instrumentation standpoint, maybe at Mauna Loa, how has that changed over time, if at all, methods, any of that sort of stuff? Because, you know, obviously, when you're taking long-term measurement, you're really trying hard to work in some sort of consistent manner so that, you know, you really can feel confident about the data that you collect and the trends that you observe. And so I'm just kind of curious from that end of things, because I know our audience is always interested in instrumentation too.
Well, the constant in all of this has been what my father set up in the very beginning, combining this liquid nitrogen calibration called manometry with infrared detection of CO2. What's changed is we're now using different kinds of infrared analyzers that have use less gas, are more stable, don't require as much calibration, but everything still needs calibrating. So the consistency over time, the painful work or the painstaking work that goes into this is really of calibration. It's a kind of a tedious, how do you really know that 420 is 420? What do you do to prove that? I mean, you're sweating details to do that. And the other thing you have to sweat is to make sure that you're not got something contaminating your measurement, that you're actually getting pristine air, that you're not influenced by cars nearby. I should say that, you know, the volcano is giving out more CO2 now than it did previously. And this doesn't interfere with our ability to get good data, because there's a lot of situations where we're not impacted from that. But we have to pay attention to that and filter the data so that we don't have contamination. And as my father did early on, but right after an eruption like this, it's a bigger issue than it is at other times.
Absolutely. Well, I can't imagine having to deal with that. At least, you know, I mean, I know there's good levels of prediction to some degree with volcanic eruptions and all that, but maybe not quite as solid a prediction as, say, a weather forecast. So we can feel for you a little bit. We can only sympathize. I can't say I empathize. Well, Ralph, I really appreciate you taking the time tonight to share your background, your knowledge with our audience tonight. Really grateful for everyone joining the program. If you enjoyed tonight's free program, we'd strongly encourage you to make a donation to support programs like these over at mountwashington.org. You can hit the donate buttons in the upper right-hand corner there. If you have thoughts about tonight's program, suggestions for future programs, please take some time, fill out the Google Forms survey that shows up in your Zoom window right when we end here. It'll also be in a thank you email that follows tomorrow. And finally, don't forget to join us next month for our program on Tuesday, June 13th. That's when postdoc fellow Jordan Torville from the Appalachian Mountain Club, he's going to be sharing his insights from his research into plant responses to shifting climate across the high elevations of the Northeast. So hope to see you there. Don't forget to register for that program. You can check out any other programs you may have missed previously over at mountwashington.org/SITM. And we'll see you all again soon. And thank you again, Ralph. Have an excellent evening.
Thank you, Brian. Thank you, everybody.
Yeah, take care. Bye, everybody.